Greetings and welcome, friends. We have been dealing with polynomials this entire chapter, and we've talked about factoring, and today is the boss fight, where you are just going to have a whole bunch of problems, and you've got to factor them, is the idea, all right? And we won't know which strategies we'll use when. Sometimes you'll have to use the punch of the AC method, or the kick of the factoring using a pattern, or the leg sweep of the factor using the greatest common factor, right? And we're just going to take these problems down like they're a pack of ninjas attacking us, and I've trained you with all of these moves, which I have. So here we go. First thing we're going to talk about is factor by grouping, which you guys actually already know how to do. It's I might write this as step 4 from the AC method. Right? You guys might remember that AC method. No, this is in your notes. If you flip a couple pages in, it's there. I'll get it to you later. Don't you worry. Don't you worry. You'll have time at the end to review and prep. So it says factor by grouping a polynomial with 4 terms. Group them into pairs. Factor the GCF out of each pair of terms, right? The first 2 terms, the last 2 terms, and then look for and factor out the common binomial factor. That's the matching parentheses. Mathing, also accurate, I guess. Matching parentheses is what our goal is. This process is called factor by grouping, which we have already been doing, and it's step 4 in the AC method. All right, so let's just do step 4. Here we go. For this part, yoink, yoink. What can I steal out of these? Looks like an x squared. Remember, I can only steal what the poorest term can afford. And between these two, I could steal what goes into 2 and 6. What divides into 2 and 6? No? 6 doesn't fit into 2. 2 does, though. And this is a plus sign, so I'm going to have that be a positive 2. 1 does fit into both, but it's not the greatest of them. I was trying to find the thing that goes into both x cubed and x squared, and it's the largest that I could take that each term could afford. So let's see, plus 2 on the outside, like so. And now I've got to figure out what goes inside these parentheses. X squared times what is x cubed? Well, x squared times x, because remember, if I multiply, I would add those exponents. 2 plus 1 is 3. And x squared times what would have been 3x squared? What are your guys' thoughts? Yeah, plus 3, right? X squared times 3 will be 3. X squared. Excellent, excellent. All right, and let's see. 2 times what is 2x? Yeah, plain old x. And 2 times what is 3? Sorry, 2 times what is 6? And I gave you the answer is 3. Crazy, Mr. Waddy. All right, and the goal is that these parentheses must match. And this is the weird idea. Watch this. If I think outside the box, I'm going to macro GCF this. Yoink and yoink. That's what's taking place. Now, I just told you to write one of those in one set of parentheses and another, and then the GCF terms from earlier in the other. But what's actually happening is, in these kind of macro terms, right, if I think of this as a term and this is a term, they both have an x plus 3 in them, and I can steal an x plus 3. Isn't that crazy? It's like, what? I'm factoring, like, but it's on this bigger level, this bigger scale that I'm factoring at. It's pretty amazing. Pretty amazing. And then what's left would have been, so I would have written x plus 3 outside a set of parentheses, and what's left would have been the x squared and the plus 2. X squared plus 2. Right, so that's the only way we know to factor a 4-termed polynomial is with factor by grouping. That's your only strategy right now. And not all problems are factorable, as we'll find out today as well. So let's see, for this one. This one's got all sorts of like x's and y's in it. This is weird. But let's see if I can find something to steal from the first two terms. That's weird. I can't. Maybe I can rearrange this? Let's rearrange this. What if I... Actually, let's write this in standard form. Sorted by x. X's, all right, is the way I'm going to sort it. Okay? So x squared would be my first term. The next highest degree polynomial is going to be this xy term, right? Because 1 plus 1 is 2, so I'm going to write plus xy, right? And then I'll write the x, and then this y had 0 x's, so it's going to go last. All right, that's interesting. Yeah, so this idea, what I'm doing is I'm writing it in standard form, which is from highest exponent. Yeah. Well, I was just saying that this is an x to the first. So notice for the x exponents, it's going 2, 1, 1, and then technically this has an x to the 0 there that is invisible because x to the 0 is 1. So I've sorted this in descending order according to the x's exponents. And I picked this one before this one because, right, x to the first, y to the first, this has a degree of 2, whereas this only had a degree of 1 when I add its exponents together. All right, now that I've done that, I'll be able to GCF yoink yoink. So between these two, x squared and x, I can steal an x. And between these two, I can't steal anything. So I'm just going to call this a plus 1. Right? Like they each had an invisible 1 in front of them, and it's like, well, I'm going to steal your invisible money. And it's like, thanks. Right? Oh, man, you even stole my imagination. So let's see. So I'll steal an x from those two and a positive 1 from these two. X times what is x squared, friends? Just x. X times x is x squared, right? I'd add those 1 exponents. And x times what is xy, do you guys think? Just plain old, yeah, so plus y. And 1 times what is x? X. And 1 times what is y? Y. And hey, my parentheses match, and so now I can macro GCF. How cool is this? Isn't this awesome that I can, like, steal entire binomials? It's like if you were a jewelry thief and you're like, you used to only steal like 1 ring at a time from the jewelry store, and then you're like, wait a minute, I can put these in a bag. I can steal so many more rings now. And don't steal, kids. But the point is, you can carry a whole lot more in a bag. Also, don't steal, kids. Yes. Touche. Wow, you should go back on this video and steal that audio bit and just like, here's Mr. Waddy saying, don't steal, kids. Pretty great. So let's see. So x plus y is going to be on the outside of a set of parentheses, and on the inside would be what's left over, the x and the plus 1. All right. So it's really factoring by grouping. You technically already know how to do it. It's got 4 terms. You do the factor by grouping thing. Yeah. All right, factoring polynomials completely. All right, here we go. It says, you have seen that the polynomial x squared minus 1 can be factored as x plus 1, x minus 1. This polynomial is said to be factorable. Notice, however, that the polynomial x squared plus 1 cannot be written as the product of polynomials. It's true. That's weird. I don't know. Maybe you guys didn't realize that. I might be able to show that to you with algebra tiles in a minute, but I'm going to keep reading in the meantime. So it says it cannot be written as the product of polynomials with integer coefficients. And this polynomial is said to be unfactorable. So here, check this out. Here we go. Wa-la-la-la. Hey, Mom. Hi, Mom. I'm on the internet. So here we go. Here's x squared plus 1. No. No, it's like I'm famous though. I'm on TV. Hi. So here's x squared plus 1, and I can't make these into a rectangle, and I can't do my trick of bringing in a positive and a negative rectangle, because if I tried this, the problem is this is x plus 1 across the top, and this is x minus 1, and minus 1 times plus 1 would not equal a positive 1. So that doesn't work. So this is not factorable. This is, or let me put it this way, it is unrectangularable. That's right. You heard me. Right, that'll be my trash talking when I'm in a Pokemon battle with someone. You are unrectangularable, and is what I'd say. Whereas x squared minus 1, notice that allows me to bring in a pair of these, and that I can change into a rectangular, more specifically a square. All right, so there you go. Some polynomials are not factorable. Okay, so even like x squared plus 2x, let's say, plus 2. Can I turn this into a rectangle? No. Man, I got one left over. Why? Right, I can't. So x squared plus 2x plus 2 is not factorable. And if I even tried factoring, right, find the factors of c, which are 1 and 2, which of those add to be 2? Well, 1 plus 2 adds to be 3, right? So if this was x squared plus 3x plus 2, that's something that's factorable. I can turn that into a rectangle. All right, cool. All right, I can't minimize that quick. There we go. Bye. All right, so a factorable polynomial with integer coefficients is factored completely when it is written as the product of unfactorable polynomials with integer coefficients. All right, what that means is it's been completely broken down beyond all breakdownability. Break it down. All right. In order to factor completely, this is a general strategy. This is a really great outline here. First thing you should do is factor out the greatest common factor, right? So that's our, here's my inkwell. Our yoink is what they did here. They factored out a 3x. All right, first thing you should do, factor out GCF, and then check to see if what remains can be factored further. The next thing you could do is look for a pattern, right? Is this one of those a equals x, b equals 2, and then 2 times x times 2 is equal to 4x, right? See if a pattern applies, right? And we've had 2 patterns so far. We had the difference of squares pattern, and we had the a squared plus or minus 2ab plus b squared patterns, right? So we've got 2 patterns. So check to see if you can use those, because those will be shortcuts. Then see if you can factor the trinomial using your, find the factors of AC, right? AC, write your factors 1 and blah, 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 1, blah, 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 and which of these blank to the b sort of thing. That strategy. And if that doesn't work, hey, maybe it has 4 terms, and maybe you can factor by grouping, which is what we were just talking about. So these are your general approaches as far as how you would do these types of problems. So let's see, this had to factor out a -4, I think. Yeah. So there you go. That's the general strategy, and that's now what we're going to try to do. I'm just going to give us problems, and we're going to try to factor it using all of our ninja moves, right? This is the day you've trained for, okay? All right, here you go. So factor completely. All right, for part A here, first thing I should do, I should have left this purple, because I'm going to check to see if I can steal something from all of these. All right, so between 3, 6, and 18, I can steal a 3 from those. And between x cubed, x squared, and x, I can steal an x from everybody, right? So I'm going to steal a 3x. 3x. So 3x outside of a 3-termed expression. a 3 and an x, right? 3 goes into both 3, 6, and 18, and x goes into x cubed, x squared, and itself, is what I'm stealing. So let's see, 3x times x squared would be 3x cubed. 3x times 2x, right? 3 times 2 is 6, x times x is x squared. What would go there? 3 times what is negative 18? It's going to be negative 6. Negative 6. I agree. All right. So I've factored out a GCF, but I don't yet know whether the inside of this can be factored further. Now, is this a pattern? Hey, that's a perfect square. Is this a perfect square? I asked the question, 3x times what would have been 6x squared? So 3 times what is 6? Or asked another way, 6 divided by 3 is what? And I got 2. And then x squared divided by x is a regular old x. Right, or x times x is x squared is the better way to do it. So I'm trying to think of, like, if I was to redistribute, what would have had to be here to give me those things up top. Let's see, this is, so negative 6 is not a perfect square, so it doesn't match a pattern. Hey, there's a positive 1 here, so I'm going to find the factors of 6. 1 and 6, 2 and 3, la la la, la la la. Let's see, which of these factors subtract to be 2? 1 and 6 have a difference of 5, 2 and 3 have a difference of 1. So none of them factor to be 2. That means this inside trinomial is unfactorable, and that means I'm done, right? This problem cannot be factored any further. All right, I factored it as far as I could. But I had to still verify that this was done. Now, if you wrote this as your answer and I didn't see this work, I would actually take off a point on tomorrow's test because you didn't necessarily verify that it was unfactorable. I'd still need the evidence of how you got to that conclusion. Yeah. So let's see here. Yoink yoink. Between 7 and 28, what can I steal? Do you guys know? 7, agreed. How about the x to the 4th or x squared? Well, I can steal 2 x's from each, right? X squared from each, so you were right the first time. All right, so let's write that down. So 7x squared on the outside. And right now, here's the tricky part. What would have been on the inside if I was to distribute this back in? This has already got the 7. X squared times what is x to the 4th? Yep. And let's see, 7 times what is negative 28? It's going to be negative. No. 4. And this one's already got the x squared, so I don't need any other x's over here. Now, I don't yet know whether the inside of this can be factored further, but hey, wait a minute. This is a perfect square. Is 4 a perfect square? And they're being subtracted. Aha. So that means A would have equaled x. What would B have been? 2, right? Because 2 squared is 4. And the pattern I'm using is a squared minus b squared is equal to a plus b times a minus b. And x plus 2. Yeah. And you could have written the x minus 2 first. That is right, to write the plus sign first. Because, hey, I'm a positive person. What can I say? You know, the glass is like half full or something. So yeah. So that's the way we factor completely is what we do. That's done what we do. Let's actually look at a few more of these. And I think for our adventures today, for this video, for the sake of my class today, this is as far as we're going to go. Now, I gave you more examples if you want to check them out. Technically, you know how to do all of them. Yeah, you technically do. But yeah, we'll just look at these ones right now. All right. Let's see. Austin. All right. So step 1 for problem 3 here. I'm trying to figure out what to do. What is my recommended place to start? Do you know? Smell like food or smoke or some... Maybe. There's like a workshop nearby, maybe. Yeah. All right. Yeah, I don't know. I'm fine if you want to go and investigate further. Well, like one of you. But yeah, I don't know. So anyways, if one of you wants to go and find out, you could, but I'm gonna keep rolling. Actually, wait, are they working outside right now? No. I don't know. It does smell a little bit like oil or something. Or oh, you know what? It smells a little bit like propane, which is a reason to be concerned. Yeah. But it's happened before, and I guess when they top off the propane tank, which is just outside here, sometimes it does have a residual smell afterwards. So I believe that is our mystery. But yeah, I'll call it in right at the end of this just to make sure. But it should be business as usual. So let's see. So Austin, our first strategy is to see if I can yoink, yoink, yoink. Yeah, so Austin and I agree. We'll take out a 3x. And Austin, what would you say would be left inside? Yeah, I agree. Okay. Let's see. Tyler, do you believe that Austin and I have fully factored this? Do you think I could take this any further? Do you think maybe could I use a pattern on this? All right. These are both perfect squares, right? X squared is x squared and 2 squared is 4. Ooh, goodness. And the pattern I can use, actually, this is exactly the same one I just had a moment ago, right? This is x squared minus 4 is going to equal x plus 2 times x minus 2. Yes, agreed. So let's see. So I'll have 3x still out front, and we'll have x plus 2, x minus 2. Like so. Yep. So let's see, my students found out that 2y can come out of this, and 2y, and this is what they're working on now, 2y times y squared, because y to the first plus y to the second, or when I multiply variables, I add their exponents if they have the same base, and 1 plus 2 is 3. And then 2 times what is negative 12 is negative 6. But I've got a y to the first here. How am I going to get that to be a y to the second? Yeah, I need another y to the first because 1 plus 1 is 2. Okay? And 2 times what is 18? 9. And I already have my y, so I don't need any more. No y's for you, but also no x's. Okay, so now as far as this on the inside, I could find the factors of 9 that add to 6, and I'd actually be able to get an answer. But I actually, wait a minute, notice these are perfect squares. Where A would have been y, and B would have been 3, right? And I'm going to have 2y times... Oh, wait. Oh, I can't use it yet. Sorry. I got to check that middle term. Is 2 times y times 3, is that question mark equal to 6y? And 2 times 3 is 6. And then, yeah, it worked out. So I can use a pattern. That's going to be way easier. We'll have 2y times, you guys remember which pattern this is? This is a squared plus or minus 2ab plus b squared is going to equal a plus or minus b all squared. So I'm going to have, this was a minus sign, so I'm going to use the minus version of this pattern. I'm going to have a minus b all squared, which is y minus 3 all squared. Like so. Let's see, and for this last one, I can steal, looks like an m is the best I can steal. So m times m squared is m cubed. M times negative 2m is going to be negative 2m squared. And m times negative 8 would be negative 8m. Now, is it possible to factor this using a pattern? No, 8's not a perfect square. The leading coefficient on this is 1, so I'm going to find the factors of 8, 1 and 8, 2 and 4, and ask the question, which of those subtract to be 2? And 2 and 4 is the answer, I agree. So I'm still going to have this m out front, and I'm going to have two sets of parentheses. I'll have an m with a 2 and m with a 4. And let's see, they've got to multiply to be negative, so their signs are either plus, minus, or minus, plus. And they have to add to be negative. So the more influential one, the 4, must have been negative. Aha! So minus and, sorry, plus and minus in the order from left to right. All right, thanks for watching, internet friends. Have a great day. Seriously, have a great day.